Have you ever wondered, why do mirrors reflect the electromagnetic waves that fall on them? To understand this, we need to examine the electric and magnetic field components of electromagnetic waves, the photons that carry these waves, and the properties of the conductive materials used in mirrors. Mirrors generally consist of a glass layer and a conductive metal coating. Conductive metals have a high density of free electrons. These free electrons are affected by the electric field component of electromagnetic waves and oscillate. According to classical electromagnetic theory, accelerating charges emit electromagnetic waves. When an electromagnetic wave reaches the surface of a conductive metal, it sets the free electrons in motion. Since the electric field exerts a force on the electrons in the opposite direction, the electrons oscillate in the opposite phase. These electrons generate a new electromagnetic wave that is out of phase with the incoming wave, thus creating reflection. But why does reflection occur at a specific angle rather than at random angles? And can electromagnetic waves of all frequencies be reflected by metal? The free electrons within a conductive metal exist at specific energy levels and oscillate at certain natural frequencies. According to the principle of forced oscillation, if the frequency of the incoming electromagnetic wave is much higher than the plasma frequency of the metal cannot effectively reflect this wave. Therefore, depending on the type of conductor, electromagnetic waves can only be reflected within a certain frequency range. To understand why reflection occurs at a specific angle, we need to examine boundary conditions. When electromagnetic waves hit a surface, the electric and magnetic field components must continue to satisfy certain conditions on that surface. The electric field on the surface must be continuous between the incident and reflected waves. The continuity of the magnetic field must also be maintained, which requires the alignment of wave vectors at specific angles. These conditions give rise to the law of reflection in optics. The angle of incidence of the incoming light is equal to the angle of reflection. From a quantum mechanics perspective, each photon interacts with the free electrons on the surface, and a new photon is emitted. However, this emission is not random. It is determined by probability amplitudes, which can be modeled using Feynman diagrams. Photons travel along all possible paths described by the path integral formulation, and these paths undergo interference, either canceling each other out or reinforcing one another. As a result of this process, the reflection law observed in classical optics emerges. In other words, the reflection angle of light is equal to the angle of incidence because the photon paths traveling in this direction dominate, while other paths interfere destructively. When all these mechanisms come together, the scientific basis for how mirrors reflect electromagnetic waves at a specific angle and within certain frequency ranges is established.